finishing off reading Alice in Quantumland, an allegory of quantum physics by Robert Gilmore. All right. So I want to welcome everybody. I want to thank everybody for hanging out with me, reading with me. Welcome, readers and scholars. I'm delighted to have you. Everybody is welcome. I don't usually read you guys on the chat, but I do read all my comments and I read the chat afterwards. So sorry if I don't say hi right away because I'm reading the book for y'all. Okay? Um, Thank you everybody that joins me. Everybody is welcome. Remember to subscribe. Remember to like, leave me a comment, whether you're watching live or on the replay. Send me super chats, gems. I'm not opposed to it. Okay, let's continue reading. This is chapter 9, uh, which we ran into from chapter 8 yesterday. Chapter 9, the particle masquerade. Remember? All right. Alice says, "You have changed color," she announced in a tone that was almost accusing. "Naturally," replied Uppo calmly. "We are usually off color. When I started, I was quite green. Then I felt a little blue, but now I am beginning to see red." "You know that particles which have electric charge exchange photons?" he said abruptly. "Yes, I was told about that," replied Alice. "Well, we quarks are colorful characters. We stick together by exchanging gluons. Through thick and thin, or rather, through red, green, and blue. The gluons stick around when they see the color of our money. They monitor our color. Particles which have color all exchange gluons. The gluons hold them together in much the same way as photons do particles with exchange. Do for particles with exchange. "But why do you change color?" asked Alice. "Charged particles do not change excuse me. Charged particles do not change their electric charge when they exchange photons. But photons do not carry charge. There is no charge on a photon, which is why they are so popular. Gluons do carry color. When a colored gluon escapes from its source, then that hue is transferred to the quark that catches it. It is a regular who's hue, I can tell you. It is a regular who's hue. Sorry, that was funny. That was cheesy, but it was funny. It's a regular who's hue, I can tell you. As Uppa was speaking, Downo exchanged his hue to blue, and Strange-O became red, his curly hair taking on a particularly vivid shade. Ooh, red curly hair. That's cute. Um, okay, here it sends us to the end of chapter note 2. Let's see what we got here. It says, "Quarks are held together by forces like, but yet unlike, the electrical interaction. These forces do not act on electrical charge, but on something else, which is called color charge, or just color. This has nothing to do with color as we normally understand it. It is just a name which has been given to something completely new. The fact that the word color is already in use is perhaps unfortunate, though it is not the first time that a word has had two different meanings. The interaction between two electrically charged particles is due to the exchange of virtual photons. The interaction between quarks is caused by the exchange of a new class of particles which have been named gluons. Hi, I am reading. Okay, let me take a short break. Ooh, yeah, so you can understand. We are reading Alice in Quantumland by Robert Gilmore. It is an allegory of quantum physics. Stick around, we'd love to have you. The interaction between two electrically charged particles is due to the exchange of virtual photons. The interaction between quarks is caused by the exchange of a new class of particle, which have been named gluons. There are different there are differences between the interactions. Electrical charges come in only two forms, positive and negative, or charge and anti-charge. The photons, which are exchanged between electrical charges, are themselves electrically neutral. They carry no charge, and so do not emit more virtual photons in their own rights. This is about quantum physics. It's explaining quantum physics in a story. All right? It's really cool. Stick around and watch the other lives on replay if you want to hear the whole story. Um, The gluons exchanged between quarks are emitted by a form of charge carried by the quarks, but completely different from the normal electrical charge. It is called color charge, though it has nothing whatsoever to do with the colors that we can see. While there is only one form of electrical charge, together with its opposite or anti-charge, there are three different forms of color charge, given the names blue, green, and red. Again, it should be stressed that these names are just conventions and have nothing to do with ordinary names. Oh, excuse me, with ordinary color. Associated with each color charge, there is an anti-color, and there are two ways of producing color-neutral objects. With electrical charge, you can only produce an electrically neutral object by combining charge and anti-charge, positive and negative charge. There are two ways to produce color-neutral particles, a combination of color and anticolor, as in bosons, or a combination of all three colors of quarks, as in fermions. Okay. Anyway, Um, let's continue reading. Maybe your morning will get better. Uppo indicated Stranger. There, he said. That is a source of a different color. It is because we have such colorful gluons that we can never be separated. One of all and all for nothing. Oh no, excuse me. One for all and all for nothing. That's strange. Um, one for all and all for nothing. Oh my goodness, where did I leave off? Oh yeah. United we stand and divided we remain inseparable. They are never divided. Um, I am afraid that I do not see what you mean at all, protested Alice. Well, we all know that opposite electric charges attract, but you can separate particles which are suffering from that sort of attraction. They are held together. They are held together by photon exchange, but the photons have no charge. If there is a no charge on photons, then oh wait, hold on. This guy has a weird way of talking. He says, if there is no charge on photons, then they free. They go wherever they want, said Downo suddenly. Right. Because photons have no charge, they are free, free to spread out as far as they want. They do not exchange other photons between themselves. If there is no change and no charge, then there is no transaction, added Downo. Thank you. Um, these photons, they they know do a business together. These photons, they know do a business together. Without charge, the virtual photons have no business with one another, so they do not attract one another. No one gets a charge out of them, so they just spread out all over the place. The farther apart the source charges get, the more place they have is for the more place there is for the photons to spread out over. The photons are spread out thin. They have a thin time of it. They have a thin time of it with less momentum to transfer. Last job, get a transfer. Cut in Downo helpfully. They say they go to give me a little momentum, but all they give me was the boot. And you felt the force of their argument, replied Uppo. But with less momentum to give, the force gets weaker. You pull charges far apart, they lose touch. The attraction gets weaker and weaker, and eventually they get so out of touch that they don't even remember to write. Give them enough energy, and you can pull them anywhere. They can get so far apart, there is no attraction left to speak of. The charges are then quite independent. I expect you know what someone means by an independent charge. Or I charge someone with independent means, for that matter. What? Let me read this one again. uh, um, The charges are then quite independent. I expect you. No, photons are neutral. Photons do not have a positive or a negative charge. The charges are then quite independent. I expect you know what someone means by an independent charge, or what I charge someone with independent means. For that matter, he added. But enough about electric charges. We are here to talk about quark charges. What's a quark charge? Asked Alice curiously, always anxious to get as much clear as she could manage. Double rate on weekends and up quarks. Double rate on weekends and for up quarks, answered Downo. But we are very cheap. Our charge only a third of other particles' charge. One thing I do not understand, said Alice to Downo. That was that was an understatement, as there were many things that she did not understand by now. Why do you try to talk as if you were Italian? I do not believe that you are. I should have given Downo an Italian accent, you guys. Um, okay. I'm going to finish this and then I'll read a little scientist blurb, all right? I do not believe that you are. It is because he is a fermion, replied Uppo on his behalf. Enrico Fermi was Italian. But aren't you all fermions? Protested Alice. Certainly, one for all and all for Polly, which nobody can deny. All three quarks stood to attention and saluted. We are one group indivisible. A quark cannot escape from inside a proton or from any other particle. This is all because of the red, green, and blue. There's old glory for you. Pardon me, began Alice. Gesundheit, answered Uppo, but Alice continued determinedly. I don't know what you mean by glory. Of course you don't, until I tell you. I meant there's a nice knockdown argument for you. But glory doesn't mean that, protested Alice. When I use a word, it means just what I choose it to mean, neither more nor less. The question is, which is to be master? That's all. But it is another question with gluons, he added gloomily. There is no master in them. They never let go. Not like the photons. The trouble is that the gluons are all colored. And color creates gluons like charge creates photons. So all the gluons emit other gluons, and those gluons emit more gluons. You start with just one or two, and you end up with hundreds. It's like having a wife's family stay, and because they all are and because they are all exchanging gluons, they all stick together, just like the wife's family. Instead of spreading out in a wide fuzzy cloud like photons, they bunch up to form the tight colored strings of virtual gluons that you see here. Because they are bunched up, they are not free to spread out like photons. There is no such thing as a free bunch. No photons, no charge. You guys, you guys, this book is making me laugh, and you guys are making me laugh. Okay, before I continue, I already finished the second page, okay? I read this, and I read this, and I skipped this and this, but now I'm gonna read this and this. These are the two blurbs of our little bald scientist, okay? Here I go with the first one. The first one says, many particles have electrical charges, and it is a striking fact that the observed particles have charges which are all of the same size. Some particles have positive charge and some negative, but the amount is the same in each case. This amount is usually called the charge on the electron, simply because electrons were the first particles to be discovered. Okay, that makes sense. Um, Estimates of the charges possessed by quarks require that they be different. A quark may have a positive charge, which is two-thirds the size of the electron's charge, or it may have a negative charge, which is one-third as large as an electron has. As quarks cannot escape from their bound groups, these fractional charges cannot be observed directly, but there is strong evidence that they are correct. And now the next blurb that our bald scientist has for us is, the existence of three different types of color allows the gluons to be colored also. Each gluon is a mixture of color and anticolor. With photons, a mixture of charge and anticharge gives a particle with no charge. But the gluons may mix different colors. A gluon may be blue and anti-green, for example. Such a gluon is not neutral. It possesses color and may act as a source for other gluons. This means that the gluons also are bound to one another and form narrow strings joining the quarks together, rather than spreading widely as do photons. All right. I'm going to show you the illustration before I begin reading, so I don't have to pause later. See, this is Alice. Remember, the reason why she's laying down like that with all the quirks, she is inside a quirk, and she's like laying down like that with with Uppo and Downo and Strango. Yes. Um, let us continue. Thanks for joining, everybody. When one quark moves away, he soon comes to the end of his tether. If we have more energy, the gluons will give us more rope, but we are still hanging on to the end of it. However far we roam, the glue-on attraction pulls us home. We cannot break free, but we can still escape with a little help from our friends. I saw Bob Marley before, but this is the Beatles for sure. With a little help from our friends. At that singularly appropriate moment, a photon of very high energy crashed into the little group of quarks. Alice had had no warning as she had not seen it coming. In fact, as she now realized, photons move so fast that she had never yet seen one coming before it arrived. This photon collided with Strango, exciting him to a quite manic frenzy, and he rushed off, honking loudly on a horn. Quack, quack. Behind him, his tether rope stretched out farther and farther. Alice could see that, however far it stretched, the rope was not becoming in any way thinner or weaker. It was obvious that it could go on stretching indefinitely, and that the escaping cork would soon run out of energy, with no chance of breaking free. Okay. But no sooner had Alice reached this conclusion than the rope broke. There was a moment before there had where a moment before there had been one long and steady lengthening cord which was soaking up all the energy that the photon had delivered. Now there were two very short lengths with a large and steadily widening gap between them. On either side of this break had appeared a new cork, each anchoring one of the fractured ends of the ropes. On the end of the rope, which was still attached to the two corks who had remained with Alice, was a cork who looked exactly like Downo, apart from being a different color. The rapidly receding Strangio was trailing his own short length of rope, to which was attached a reversed version of Downo. This Alice assumed correctly to be an anti-cork. Whatever has happened? Asked Alice in some confusion. You have just seen a cork escape with the help of friends in low places. In the vacuum, in fact, and you can't get much lower than that. You cannot detach a glue-on rope once it has seen the color of a cork. So we have to fool it with something which looks like just like a cork. And what is that? Asked Alice. Another cork, of course. When the glue-on string has stretched long enough so that it now contains enough energy to create the rest masses of two corks, then we cut the string and work the switch. One end gets a new cork and the other not. There is a knot in the string? Asked Downo, one of the Downos. That's right. There's a cork at one end, not a cork at the other end. What's not a quark? Asked Alice. An anti-quark. And if you believe that, you should see my uncle. Part of the original string, part of the original string has vanished rapidly into the distance, carrying off the energy and connecting the absent stranger to the new anti-quark. So you see, absence makes the part go younger. No, excuse me. So you see, absence makes the part go yonder. He may have escaped, but he still isn't free, protested Alice. With a bound, he was free. With a bound, he was free. He is free of us now, but he is still bound. With his anti-quark, he is bound into a boson. That's like a pion, but pions can be deceiving, and in this case, they have formed a kaon. Kaon instead. You do not see a free quark, or even a free or even free a quark at a quark C. You do not see a free quark, or even free a quark C. But that's another kettle of fish. Are the fish in okay. Are the fish in Quark Sea? Asked Downo. No, there's nothing fishy about the Quark Sea. Its sole purpose is to hold virtual quark-antiquark pairs. The soul I understand, and the purpose I understand, but why the pairs in the sea? Argued Downo. Forget the sea, replied Uppo, or we will be at the sea. The point is that you will never find a quark on its own. And now we will see the end of chapter, note 3. Note 3. Here it is. When particles are bound together by the electrical interaction, the potential energy in the binding decreases rapidly as they move far apart. If a particle is given enough energy, it can break free completely, as a rocket which has reached the escape velocity has then enough energy to break free from the Earth's potential. When a gluon string has already been stretched, however, it takes just as much energy to stretch it a little further as it did initially. It is like stretching an elastic string. It doesn't get any easier the farther you stretch it. It is also like an elastic string in that when you stretch it, it can break. Mm. Does that mean that you have to stay here forever with no chance of a change? Asked Alice in concern. Oh, we can have a change, all right. We say a change is as good as a rest, but I feel quite at liberty to discuss the weak interaction. I heard that mentioned when I was visiting the nucleus. I believe it had something to do with beta decay of nuclei, whatever that may be. It is the same thing. In fact, it is a far, far beta thing. What happens is that a neutron inside the nucleus changes into a proton and an electron together with another particle called a neutrino. This neutrino has no charge, no mass, and no strong interaction. It doesn't do much of anything, really. Like most of the folk I know. Anyway, that's the story we tell. What really happens is that a down quark inside the neutron changes to an up quark, an electron, and a neutrino. When the down quark changes to an up quark, when everything is on then everything is on the up. It puts the charge up, the neutron becomes a proton, and there you are. Hang around, and you might get lucky. Hardly had he spoken when, by a most convenient coincidence, one of the two Downos became blurred and began to change and lose his identity. After a fleeting moment of transition, Downo was no longer there, and in his place stood a duplicate of Uppo. As he moved aside, Alice saw an electron rush away from the same spot. This was followed by yet another particle. Alice caught only the briefest glimpse of this one, something barely perceived and very hard to see at all. This she assumed to have been the neutrino, performing its usual role of ignoring and being ignored by everything and everybody. The group of three quarks now consisted of one downo and two identical uppos. Identical, that is, but for the fact that one was currently green and the other blue. My, said Alice, that was a most remarkable thing altogether. Obediently, the two uppos replied in perfect unison. What was the most remarkable thing? Oh, what? Wait. Obediently, the two uppos replied in perfect unison. That was a most remarkable thing. But what can you expect? They added. When the particles exchange in an interaction have what can you expect when the particles exchanged in an interaction have an electric charge? Photons don't have a charge, but this isn't the charge of the light brigade. When a source emits one of these charged particles, it has to charge. Oh my god. Oh my. It has to charge the charge. There are no functions allowed there. There are no fluctuations allowed there. When the particle's electric charge has changed, then it counts it as a different particle. You must have heard of charge accounts. That is how the weak quarks get to change, they added. But where does the electron come from? Asked Alice, who felt that the explanation was a little lacking. The particles exchanged in the weak interaction are called W, began Uppo rather inconsequentially. What? Responded Alice, temporarily forgetting her manners. Not what, just W. It is not much of a name, but it is all they have. Poor things. There are two of them. One is W plus and one is W minus. No one has ever asked them what the W stands for. He finished thoughtfully. Anyhow, he continued, there's W's, as their friends call them, uh, these W's, as their friends call them, are very friendly types. They will mix with anyone. They interact with both leptons and hadrons, with electrons as well as strongly interacting particles. So when a down quark decides it is time to change into an up quark, it gets all charged up. The electric charge of the quark has increased, so it gives out a W minus particle to balance the books. This W, in turn, plays it by the book and interacts with a passing neutrino, which has no electric charge at all, turning it into an electron, which does have an electric charge. The electron finds itself in company with a lot of strongly interacting particles, where it has no right to be, and leaves as rapidly as it can. And now let's go see the end of chapter note 4. Cuatro. The masquerade. Oh, excuse me. Though the quarks cannot escape from the particles within which they are bound, they can change from one type to another. This is caused by a peculiar process called the weak interaction. The weak interaction is a broad-minded process which will interact with virtually everything. The electromagnetic interaction affects only particles that have an electric charge. The strong interaction affects only the strongly interacting particles, or hadrons, and not leptons. The weak interaction will affect them all, though the effect is rather slow and weak because it is a weak interaction. The weak interaction is peculiar in that it can change quarks. It can change either a down quark or a strange quark to an up quark. In the process, the electric charge of the quark is changed, with the surplus charge carried off by the W boson, the type of particle which is exchanged in the weak interaction. This charge may then be handed over to newly created leptons and an electron and a massless electrically neutral lepton known as an antineutrino. This happens in the process of nuclear B decay. It's not really a B, it's the um, Greek character that looks like a B, in which a radioactive nucleus emits a fast electron. This process had been known for many years, but was odd in that it was quite clear that there was not any electrons available within the nucleus to be emitted. The electron is created in the decay process, and, as it is not bound, leaves the nucleus immediately. Uh-huh. All right, so we may finish this chapter yet. But where does the W find a neutrino, which it can change into an electron? Asked Alice in some puzzlement. I didn't think there had been a neutrino there before. I thought that it was emitted after the decay along with the electron. Ah, that is where it fools you. You thought it should have, you thought it should be there before, but instead it was there after. You are expecting it to arrive from the past, so it sneaks up on you, back from the future, and still arrives when it is needed. Of course, because it came from the future, it is still around afterwards, on its way to arrive. In this way, it gets to be both the neutrino converted by the W and the one emitted after the decay. That cuts down on the overheads. But how can it arrive from the future? Asked Alice. As she spoke, she had a distinct feeling that she already knew the answer to this question. Me too. It is an anti-neutrino. Of course, one of my favorite antis. Every particle has an antiparticle, which travels backward in time, and so is opposite in every way. That's the great principle of antiparticles. Whatever is, I'm whatever it is, I'm aging it. Whatever it is, I'm aging it. Um, and is there no way any of you can ever get free? Asked Alice, to be quite sure on this point. No, no way at all, they assured her. Does that mean that I cannot escape either? Asked Alice in dismay, as they did not really wish, as she did not really wish to be trapped with them forever. Not at all. You have no color, so the gluons don't hold you. You are one of the most colorless people we have ever met, so there is nothing to keep you. You can leave whatever whenever you wish. We won't even notice. You can get up and walk away. Just don't forget to leave a tip. Don't forget to leave a tip. Readers and scholars, come read with me and tip me. Or don't. You're welcome anyway. But I do want tips. Um, this sounded much too simple, but Alice tried it anyway. She stood up and found that, indeed, there had been nothing to prevent her from leaving the group at any time. She stretched after her cramped confinement in such a small space, looked around her, and found that she was standing face to mask with the master of ceremonies. His grinning mask was just a few feet from her face. She stared at him, hypnotized by his wide, fixed grin. The dark eye holes above, deep within their black depths, were his eyes, where his eyes should have been. She thought she could see an intense blue spark, like a distant star on a clear, frosty night. And how did you enjoy your meeting with the Quarks? He asked her merrily. It was very interesting, she replied truthfully. There were most colorful characters, but I did find them rather changeable. Was that the last unmasking that will take place tonight? Alice continued. Or are there further layers to be stripped away before I can see what is really there? Who can say? He replied. How can you ever know if you are finally looking on to the naked face of nature, or if you are simply looking at yet another mask? Tonight, however, there is but one more unmasking to come. I have yet to remove my own mask. As he was speaking, the bright spotlight, which had followed him all through the evening, began to dim, and the light from the chandeliers overhead became even fainter than it had been before. As the light died, the master of ceremonies lifted both hands to his face and slowly pulled off his mask. In the rapidly fading light, Alice looked at the face behind the mask. She could see nothing but a smooth oval, a total blank with no features of any sort discernible. She stared in astonishment at this enigmatic visage, and as the last gleam of light died, she saw the mask wink at her. He took off his mask and there was nothing underneath, but the mask winked. Wow, that's really cool. We ran out of time and we ran out of chapter. It's Friday today, y'all. I am not gonna read this weekend. I'm too busy. But Monday. Monday we may finish the book. And if not Monday, Tuesday. I'll see you all again. Love you. Love you. Mwah. Take care, readers and scholars. Come back again. Subscribe if you haven't subscribed. Hit the notifications, but most of all, come back. Come read with me. Bye bye bye.